everyone. Welcome to lecture 8 of Mathematical Modeling and Simulation. So let's begin. In this lecture, we are going to look at what is scaling in mathematical models. So firstly, I'll begin by giving you a general introduction about scaling, and then specifically we'll discuss about geometric scaling, scaling in equations, and the effect of size, and this we'll study by taking a particular example from industry. What is scaling? Scaling is one of the techniques used in the process of mathematical modeling. So if you recall, in our initial beginning lectures, I told you that in the process of mathematical modeling, there are four methods. The first one was dimensional analysis, which we have already done. The second is scaling, which we are currently discussing. So this is one of the techniques in the process of mathematical modeling. Subsequently, in our coming lectures, we'll be discussing the third and fourth also. But right now in this lecture, we are going to focus on scaling. So to understand it better, let's have this example of an equation F equals to minus kx. This is the famous spring mass equation in which a mass of particular mass is tied to a spring and given some displacement, and then its motion is discussed. So this equation is used to model the dynamic behavior of tall buildings in their response towards earthquakes, while it's also used to model the motion of a small diving board. So a small diving board is an example at a small scale, while tall buildings are an example of a large scale. So K can distinguish between different scales. So that means this K stiffness constant, which depends upon many properties of the underlying material being used and so many other factors. So that factor is sufficient to capture the details at different scales. However, the main idea of understanding this example is that one single equation can be used in a small scale model as well as it can be used at a large scale model as well. Obviously, the parameters can have different values at different values or different scales, but the same mathematical model can play its role even when the model is at a small scale or it is at a large scale. So that's the fundamental concept of scaling, that when we move from small scales, when we move from smaller objects to higher, bigger sized or large size objects, what are the changes in the underlying equations or the mathematical parameters. So that's all about scaling. And now to specifically discuss about geometric scaling. So here I'll give you the idea, and this is something which you already know, which we have already studied in our school days, the concept of geometric scaling. So to understand it from a layman's point of view, you can imagine it in this way, that suppose you are given the task of building a aeroplane, building a real aeroplane, then obviously howsoever theoretically strong you are, howsoever knowledgeable you are, but you will not be directly start constructing the big aeroplane. You'll start by first making a prototype or a small abstract version of the big aeroplane. So that means you will scale down your parameters which you actually need to have at the bigger scale. You will scale down them to a smaller scale and then work at the small scale. But the underlying principles or the governing equations are not going to change. They will just scale up or scale down according to the parameters. So that's the fundamental crux of geometric scaling. But here I'm going to give you a very simple example to understand. Suppose you have a small cube and say a bigger cube. Say the length of side of small cube is 1 unit, while for bigger it is L units. Then the surface area we know is 6 square units, volume is 1 cube units, while for bigger cubes it's 6L square and the volume is L cube. So that means what? So that means the surface area is depending upon the length. The L is the controlling parameter. So L is your scaling parameter, you can say. As you move from small cube to big cube, there is some parameter which is controlling how the physical quantities, how your measurable quantities are going to change. Measurable quantities means they can be any, but here they are surface area and volume. So this means surface area is scaling with a factor of L square, while volume is scaling with a factor of L cube. That means on doubling the length of side of the cube, the surface area is going to become 2 square, which is 4 times, while the volume is going to become 8 times. So that's the basic idea of geometric scaling, and plenty of more these kind of examples can be created and discussed. So now let's move to second kind of scaling, which is scaling in equations. So I'll directly explain this to you with the help of an example. So the question is, for what values of x, sine hyperbolic x is approximately equal to e raised to power x by 2. And the formula for sine hyperbolic x is this. So that means this is going to be true if e raised to power minus x, this factor is negligible in comparison to this factor, because we want this factor to dominate. You are asked when does the sine hyperbolic x is given by e raised to power x by 2. So this is only going to happen when e raised to power minus x is negligible in terms of in comparison to e raised to power x. Now we need to determine for what values of x this is going to happen. So by hit and trial, we start with x equals to 1 and c e raised to power minus 1 is 0.3678, e is 2.7182. X equals to 2, you see the difference is becoming larger, while for x equals to 3, the difference between e raised to power minus 3 and e raised to power 3 is reasonably large. And if you go for 4, it will be even larger. So you can say that the difference between e raised to power x and e raised to power minus x is increasing, and they are e raised to power minus x is negligible in comparison to e raised to power x for all x greater than equals to 3. So that means your approximation is valid for all x greater than equals to 3. So that's your answer, and that's what the question was asked. But in this procedure, we have not used or introduced any kind of scaling method. So now let's introduce a scaling parameter and see how the things are going to change, how the answer is going to be controlled by that. So now I'm introducing a scaling parameter. So in the original formula, sine hyperbolic x equals to e raised to power x minus e raised to power minus x by 2, you change x with x by lambda, where lambda is a scaling parameter. So now for lambda equals to 1, this is the same expression. So we have already done calculation that this is going to happen for all x greater than equals to 3, while for lambda equals to 2, this is going to happen for all x by lambda, means x by 2 greater than equals to 3 means x greater than equals to 6. So you can see that with the introduction of a scaling parameter, we have changed or we have controlled the values of x for which the given approximation holds. So that means if you want an approximation or an equation to hold for bigger domains, you can introduce a scaling parameter there and get your answer like that. So if you do the calculations for different values of lambda, you will see that every time you're getting a different answer for the different values of x. So thus, by changing the value of scaling parameter lambda, we can control the range of values of x for which a given equation or approximation holds. So that's the meaning of scaling in equations. Here I have taken a very simple example, but this technique is very frequently used even in higher level or bigger level models. Basically, you should be just clear with it that when the scaling parameters are introduced, how the equations are going to change with the introduction of those scaling parameters and how they are going to affect the solutions of this. And many times it's easy or it's better to interpret the solutions in terms of the scaling parameter. So instead of for x greater than equals to 3, now I'll be talking about the case for lambda equals to 1. So now let's visualize all these things which I have just shown you mathematically. So you can see in front of you three graphs. All the three graphs contain two curves. The first one contains four curves because it's giving you for lambda equals to 1 and lambda equals to 5. Right now I'm just focusing on the curves lambda equals to 1. So one curve is of the sine hyperbolic function, another curve is your approximation e raised to power x by lambda by 2. And this the same graph is there in all of these three, but still you can see by looking at the shape of the curve that there is something different in the three curves. So let's try to understand that. For lambda equals to 1, we know the calculations are just being done. This is approximately equal to this for all x greater than equals to 3. So you can see from A that for greater than 3 they are equal, but for x less than 3 there are differences in the graphs. Difference is small. But if you look at this graph, the difference is almost 0. Because you cannot distinguish the two curves, which one is of sine hyperbolic and which one is of exponential. So as depicted in this graph, the difference appears to be 0 between sine hyperbolic and the exponential curve. But if you look at the third graph, the difference is huge between the two curves, the dotted line and the solid line. So why this is happening? We are in the three curves representing the same data, the same information, but why a different interpretation is coming from three graphs? So we need to answer that. So this is happening because of the difference in horizontal scales. You can see in graph A, the horizontal scale, the difference is 0.5. In graph A it's 0.5, graph B it's 10, graph C it's 0.05. So depending upon how you are chosen your horizontal scale, your interpretation or your presentation of the graph is completely different. The curve is still the same, but by appropriately choosing a particular scale, you can show the result which is there. So this is how important it is to choose the scale appropriately so that the results are not misleading, because in C graph it is appearing the difference is huge, in graph B it is appearing the difference is 0, while graph A is the appropriate representation for representing the differences because it's matching with our theoretical predictions that for greater than x greater than equals to 3 the curves are almost matching, while before that there is a difference between the curves. So that's the another conclusion, that you have to choose your scales very appropriately while graphing your results. Now let's finally go towards the third example, which is effect of size. So this is an example taken from industry. So you can see here it's a Kisan mixed fruit jam. If you buy a 500-gram packet of it, so the cost you have to pay, the price you have to pay is 150, while for 1 kg it's 270. For 500 to 1 kg the weight is double, but the price is less than double. So why this is happening? So this you have often wondered, that if you tend to buy the bigger packings, you tend to save some money. So the definitely price is increasing when the weight is increasing, but the price per unit is decreasing. Instead of the price going from 150 to 300, it's going from 150 to 270. So you will tend to buy the bigger packing. So now we'll justify it mathematically why this is happening. So to understand this, let's look at that what it takes to cost of product. So product means, say you have jam and the packaging of it. So obviously if jam quantity is doubled, the price of the jam, because here we are just talking about the ingredient inside the packet, that is definitely doubled as well. So that means saving is done from the packaging. So the cost of packaging we need to look at. So we need to define the wholesale price is sum of A plus B plus C plus D, where A is the cost of producing the product, B is the cost of packaging the product, C is cost of shipping, while D is cost of packaging material. Do not get confused between B and D. B is cost of packaging is having a different sense. It means that how much time or how much machines are employed in packaging procedure. It means the closing of lid, the applying of labels or whatever it takes to pack a product. While D is the cost of packaging material exclusively. A is the cost of producing the product. That means whatever recipe or whatever ingredients are required, they are being mixed in the machines. So whatever is the production process is there, that is to be followed. So that's how briefly we have categorized the total cost as a sum of these four costs. Now let's look at all of these one by one. A is the cost of producing the product. Clearly, A is proportional to weight of the product. B is the cost of packaging the product. This depends upon the time taken to fill the packing and the time taken to close the lid, close the package, and the time taken to ready the package for shipping. That means putting it into the shipping box. Now the time taken to fill the package clearly is proportional to the weight, while the other two times, close the package and ready for shipping, they are negligible. They are not dependent on weight, or you can say they are constants. They do not depend upon whether the packing is small or big. So B you can say is having this expression. It's one factor. It's proportional to weight. So there's a constant of proportionality multiplied with weight plus some constant. So constant means this time, which does not depend upon weight. So whether you're closing the lid of a smaller bottle or you're closing the lid of a bigger bottle, it takes equal amount of time or effort. So that's why these two kind of times are not dependent on the weight. And similarly, you have obtained an expression for A. So we have obtained an expression for A and B. So let's do the same for C and D. C is the cost of shipping. That clearly depends upon weight because bigger packing need require more space. D is cost of packaging material. So D is dependent on the proportional to the surface area of the packaged product. And surface area and volume or weight you can say are connected. So the cost D is a bit different in some sense because the first three costs A, B, C were clearly having direct proportionality with weight, while this D is not having direct proportionality with weight because it has to do with the packaging material, the surface area which you have to cover with your wrapping paper or whatever material you are using for packing. So instead of depending directly on weight, it is depending upon surface area. So now we'll establish a connection between the surface area and the weight through volume. So surface area proportional to L square, length square, volume is proportional to L cube. This gives you surface area proportional to V raised to power 2 by 3. Which ultimately gives you D is proportional to W raised to power 2 by 3 because volume is also directly proportional to weight. So therefore D is given by some constant times weight raised to power 2 by 3. So surface area we came to volume, volume proportional to weight. So every four kind of cost A, B, C, D are obtained now in terms of weight. So now if you add all of them, if I rewrite all of them, you add all of them, P is A plus B plus C plus D, you'll get to have this expression which you can write in a simple form, x times x plus yw plus zw raised to power 2 by 3, where x, y, z are these parameters. So this is the price, wholesale price of the product and its dependency on the weight. So it's clearly directly proportional, means bigger packing will cost more, obviously, because remember this jam example which we just did, 500 gram you were getting in 150 while 1 kg you were getting in 270. So the price has definitely gone up from 150 to 270. But the idea of discussing this example is not price, but price per unit, which is P by W. So P by W, if you do, you'll get this expression, which clearly indicates that P by W decreases with increase in weight or size of the product, because now you can see here in this expression P was directly proportional to W because the positive powers of W were coming, while in this expression the negative powers of W are appearing. So it's inversely proportional to weight. That means if the packing size is going to increase, the price per unit is going to decrease. So that is the mathematical justification of the same thing which I told you in the beginning, that you will tend to save money if you are going to buy bigger packing. So now let's elaborate this in a bit more detail. Now we know that price per unit weight is decreasing with increase in weight. But at what rate this is decreasing? How this is decreasing? We are further want to analyze it. So for that I need to compute the rate of decrease of P by W with respect to W. So that means I'll be computing the derivative d by dw of P by W. So it's very easy to differentiate and you will get this expression, which you can clearly see is negative because all other parameters are positive. So since the rate of decrease is negative, so that means okay, decrease is happening, but it's happening at a lesser rate. That means the benefit or savings are more when the size is increased from say a certain size 1 to certain size 2, it's doubled, than when it is increased from 2 to 4. In other words, the benefit in price per unit which you will get while moving from 500 gram to 1 kg is more as compared to the benefit which you will get by moving from 1 kg to 2 kg. So that means the price per unit is definitely decreasing with an increase in size, but how much it is decreasing, that really depends upon at what level of weight you are. That means if you're moving from very small package to its immediately next package, the benefit is more, but as you keep on increasing the package size, the benefit also starts decreasing. So that's the idea of this industrial example, which might have given you much more idea about this kind of case studies. This kind of mathematical models are very useful in evaluating or identifying that how the price should be set, or so that the company is going to be in the benefit. So that's all about scaling. In our next lecture, we are going to look at conservation laws.